Hello dear colleagues. So today on this seminar we will solve some tasks that are related to the detection of ionizing radiation, and we will see how different parameters of the energy of particles, or the position of the source of the ionizing radiation and detector, how all these parameters affect the resulting count rate of our sample. So I will remind you this equation that the count rate that we measure is dependent on the parameter of the radionuclide, the yield of the certain decay type in the decay scheme. Then there is detection efficiency, of course the activity of the sample, and the background count rate. We also, when we would like to calculate the absolute activity, we also have to have in mind that the real count rate depends on the measured count rate with this ratio, where this tau letter means that time that is a specific parameter for a detector. This coefficient phi, or efficiency of the detection, depends on several parameters. I will write them here. Okay. And Q. So the first parameter is the efficiency of the detector. So it's just the parameter, specific parameter of the detector. This tau is a geometry coefficient. How we can calculate it? It's just a simple representation. If there is a source of our ionizing radiation, the radiation is released in all directions, so it goes in the shape of the sphere. And, for example, there is our detector. And the distance between the sample and the detector is just radius of the sphere. And let's say we know the area of the detector. If we know the distance between the source and the detector, and we know the area of this window of the detector, when we can simply calculate this parameter as a ratio of the area of the detector and the surface area of the sphere. So it will be our geometric parameter in the simple case. In some cases, for example, when we use liquid scintillating detectors, so it is our cocktail, and we put the radioactive source inside the detector, that means that in this case geometry parameter is equal to 1. Also, if we have a detector and the sample that is directly contacted with the detector, in this case, we have the half of the ionizing radiation that is going directly to the detector, and the half of the ionizing radiation that goes in another direction. And in this case, the geometry parameter will be 0.5. You can see that in many other cases, like in this case, the geometry parameter will be less than the half, than the 0.5. Okay. So this is the attenuation coefficient. We already solved some tasks to calculate the attenuation of the flux of the particles. I will just remind you that K for beta particles is equal to exponent in degree the attenuation coefficient, mass attenuation coefficient multiplied by the thickness of the air or window of the detector. Normally, if we have a sample here, we have a detector here, and we have this window of the detector. So we have a distance, let's call it D1, between the sample and the detector. And we also have this thickness of the detector window, let's call it D2. When we will calculate the attenuation coefficient in this case, we should calculate D as a sum of D1 plus D2, or as a sum of these two distances. Then, if we have a fixed sample, for example, this is a fixed sample. The thickness, let's call it ds. That means that part of the radiation that is released inside the sample will not go to the detector, but will be absorbed inside the material. In the case of the fixed samples, we should to calculate the self-attenuation coefficient, this S, self-attenuation coefficient. And we can calculate it as 1 minus exponent minus divided by okay. And the last coefficient, it is the backscattering coefficient. What does it mean? It means that part of the radiation which should go to another direction, not to the detector, this radiation can be backscattered from the surface of the background and will go to the detector. So we already took into account the loss of this direction by geometry coefficient, but this radiation is going by backscattering to the detector, and thus we get the higher count rate that we expected. And thus, normally this backscattered coefficient is either equal to 1 or more than 1. So, taking into account all this consideration, all these parameters and formula, we will now solve several tasks. Okay, now the task. There is a sample of thallium-204, and the measured count rate of this sample is 80 counts per second. This abbreviation CPS means counts per second. So the question is to calculate first the registration coefficient and to determine the activity, so the absolute activity in becquerels of the radionuclide, means thallium-204, if the resolution time is this number, the background counting rate is 30 counts per minute. Please take into account that here it is second and here is minute. The distance between the sample and the counter is 2 centimeters. The counter window thickness is 4 milligram per squared centimeter. The thickness of the sample itself is 40 milligram per squared centimeter. And the geometric factor is 0.06. All the other correction factors, all these other parameters are taken equal to 1. And there is some certain parameters specific for thallium-204. It is the maximum range of the beta particles emitted by thallium-204 and this mass attenuation coefficient. First of all, if you will look at this thickness or the thickness of the sample or the thickness of the counter window, you will see that there is not a usual unit like centimeter or meter or millimeter or whatever, but it is milligram per squared centimeter. What is that? Normally, if you will look in the databases, in special tables, you will find this coefficient, mass attenuation coefficient, in this unit, centimeter squared per gram. To make it usable for normal distances like centimeters, you have to divide, or in this case, you have to multiply this mass attenuation coefficient, mu. I will write it here. Mu linear will be equal to mass attenuation coefficient multiplied just by the density of the material. It is very useful, very convenient to have only one coefficient, mass attenuation coefficient, and then if we will go to another material, we just multiply it by the density of this certain material, and thus we will get the linear coefficient, attenuation coefficient that is expressed in centimeters minus 1. In this case, the thickness of the material, let's call it D, is equal to the linear size or linear thickness divided by the density of the material. So, again, if we will use this equation, And if we will use the units of mass attenuation coefficient, centimeter squared per gram, and then we multiplied it by d in milligram per squared centimeter, these units will annihilate each other, and thus there will be no units, and it is correct to use a number without units when we use them in the degree of the exponent. Okay, so now first of all we have to calculate the registration coefficient, and I will write it here again. This registration coefficient is equal to multiplication of all these factors. So it is at KSQ. What we know, there is a geometric factor that is given to us already, so it is 006. Okay, it is easy. Then there is nothing said about the detector efficiency, but there is an information that all the rest of the correction factors are taken equal to 1. It means for us that this efficiency is equal to 1. Also, there is no numbers for backscattering factor. That means it is also equal to 1. And for us, it means that we only have to calculate at the moment the attenuation coefficient and the self-attenuation coefficient. Let's start with the self-attenuation coefficient, as far as it is only 1. Thickness of the sample, it will be a bit easier. So self-attenuation coefficient, it is 1 minus exponent minus mu and d of the sample, so it's thickness of the sample, divided by mu d of the sample. Thus it will be 1 minus exponent in the degree of 28 centimeters squared per gram, multiplied by the thickness of the sample, and you can see that it is 40 milligram per squared centimeter. So that's why we have to go from milligram to grams, and we simply multiplied it by this coefficient 10 to minus 3, so it is coefficient of gram per milligram. Okay. And we will divide this by this number. Again, it is 40, 10 to minus 3. Okay, let's calculate it together. So I got this number 0.685. Okay, then we have to calculate the attenuation coefficient. Okay, that is equal to, so we can write it here. Exponent minus mu d, and in this case it is d1 plus d2. Thus it is exponent in the 28, and here's the distance to the counter, that is 2 centimeters. And we have to express it not in centimeters, but in this d value. So we have to multiply these centimeters by the density of air, because distance between the counter and the detector is filled with the air, thus the material is air, and we have to use the density of air that is equal to 1.29 milligram per cubic centimeter. And as far as it was the centimeter squared per gram, again we have to multiply it by this coefficient. And then we have to add the counter window thickness. It is 4 milligram, so we also multiplied it by 1000, and that's it. So we can calculate this. Okay. Now we have this number. And to calculate this registration coefficient, we have to multiply all these numbers. And we will have like this 3, 6. I will just check if I calculated the first number correctly. Yeah, okay, it's correct. And now we will remember this equation, that the absolute activity, it is 1 divided by yield of the decay, and for us it will be 1. This registration coefficient we already calculated, but we have to use also the correction for resolution time. So it is our measured count rate divided by this expression. And we also have to subtract the background count rate. So let's put all the numbers in this equation. We have measured count rate 80 CPS. So it is second minus 1. The resolution time is quite small number, multiplied by 80 seconds. And for the background, we have 30 counts per minute. And thus we have to recalculate it in counts per second as well. And it is easy to calculate because we have to divide it just by 60. That means 60 seconds per minute. And so we will get this. And thus we can calculate the absolute activity of our sample. And finally, I have this number, 2,6,3. As far as the whole count rates now in CPS, counts per second, it will be 2,263 becquerels. Okay, so we have solved our task. We calculated the registration coefficient, and we calculated the absolute activity of the sample. So you can easily see how different parameters, for example, the thickness of the sample, the distances between the count rate, the thickness of the window of the detector, how they affect on the final registration coefficient and on the activity that we calculated. And also, it is interesting that the registration coefficient is quite small, even if the activity of the sample is quite high, 2000 becquerels. But when we measure the sample, it is only 80 CPS, counts per second. So that means that it is quite a good example of how the measured count rate is different from the real activity. And now the next task. It will be very close to what we had. And we will need additional parameters in this case. So we will have a mixture of two radionuclides simultaneously present in our sample. And so let's go to the task. The count rate of the thin sample of strontium-90 initially purified from the daughter radionuclide. And the daughter radionuclide, as you can see already, it is yttrium-90. We measure the count rate with a detector with thickness of the window of 3 milligram per squared centimeter, and the distance again between the sample and the detector is 2 centimeters. And we have to estimate the sample counting rate after certain time, 64 and 128 hours. If the count rate at the initial moment when the sample was purified, if at this moment the count rate is 3600 CPM, so counts per minute. And we can just not take into account the correction for the resolution time of the detector. So, how to solve this task? First of all, again, we have to write this expression that the count rate that we measure, as far as we can neglect the resolution time or the dead time for the detector, we can simply write this equation from the sample plus background. And also, there is a very convenient point for us that this count rate that is measured is already given for us after the subtracting of the background. So we can neglect this. Just simply and use only this simplified equation. So we can write again this registration coefficient as multiplication of all these parameters. As far as both of these radionuclides are located in the same sample, and the efficiency of the detector will not depend on the energy of the emitted beta particles, we can say that these parameters, efficiency of the detector, the geometric parameters, because they are located in the same sample, will be the same for these two radionuclides. And also, we can guess that the backscattering coefficient will be also the same or equal to 1. Thus, the whole registration coefficient will depend only on the attenuation coefficient and the self-attenuation coefficient. So, what we can write in this case? We can write that the count rate of strontium, and also, I forgot that the probability for these two radionuclides is equal to 1. So we can simply write that for strontium, it will be attenuation coefficient multiplied by the self-attenuation coefficient and multiplied by the activity of the sample. And for yttrium, the equation will be the same, but only the coefficients will be different. But here is activity of strontium, and here will be activity of yttrium. We can calculate all these coefficients, and from this we can calculate the activity of strontium. So let's write it like this. That activity of strontium, it is the count rate of strontium divided by this coefficient that are corresponding to strontium. Okay. But what about the activity of yttrium? We know that initially there was no yttrium in the system. Thus, this count rate of the sample, that is equal to 3600 CPM, it is the count rate attributed only to strontium. Thus, we can take this number to calculate the activity of strontium. I will not correct it 2 seconds, because at the final stage we have to calculate the count rate of yttrium, and we calculate it as CPM as well. And I will write this coefficient for strontium here. Okay, but again, what about the activity for yttrium? And it is quite simple. If we will look on the half-lives of these two radionuclides, we will see that the half-life of strontium is much longer than the half-life for yttrium. That means that in this case we can observe the secular equilibrium. And thus we can calculate the activity of yttrium from the initial activity of strontium that we can calculate from this, multiplied by this expression. Let's take the degree of 2. And it is time divided by the half-life of yttrium, 19. Okay. Let's take already let's calculate or relationship between the activity of yttrium after 64 hours. It will be the case number 1. We can use this equation, and we can clearly see that after 64 hours it will be only 1 half-life of the yttrium. That means that all this expression will be equal just to 0.5 multiplied by the activity of strontium. We can write it here also. And in the case of second time, we can write it as activity strontium initial activity of strontium multiplied by 1 minus 2 in the degree of minus 2. Thus, it will be 0.75 of activity of strontium 0. The activity of the whole sample, A1, let's say, it will be the sum of activity of strontium plus activity of yttrium. It will be activity. But the count rate, we cannot neglect these coefficients. So it will be count rate for strontium and count rate for yttrium. The same is for the second case. Why I wrote here just the initial activity of strontium? Simply because this time, 64 or even 128 hours, is not enough for strontium to decay in significant degree. So only a small amount of strontium will disintegrate. Thus, we can neglect the change in the activity of strontium. So, now we can express the activity of, or not activity, the count rate of yttrium. Sorry. The count rate of yttrium as the coefficients for yttrium multiplied by the strontium count rate divided by the coefficients for strontium and multiplied either by 0.5 or by 0.75. So now we have to calculate the coefficients for strontium and for yttrium. And we will use the already known equations. We know the window thickness, we know the distance, and we know the mass attenuation coefficients. So it will be simply minus for strontium 35 centimeters per gram multiplied. Here it will be again the sum of two distances. It is thickness of the detector window. So it is 3 milligram per centimeter squared, plus the distance between the detector and the sample, 2 centimeters, multiplied by the density of air. So it is milligram per cubic centimeter. We should multiply it by 10 to minus 3. And thus we will get, so it is 0.82, let's say 26. We can easily calculate it for yttrium also. So it will be the same, but we will have mass attenuation for yttrium. So all this equation in brackets will be the same, but we will have exponent in 4.45 and written. So we will calculate this. Okay, we got these numbers. And now we have to calculate the self-attenuation coefficient. Okay, I will write it shortly. So it will be 1 minus 35 multiplied. So the thickness of the sample. Okay, it's a thin sample. I forgot that it is a thin sample. Thus, it is even more easy. We just take it as 1. For thin samples, the self-attenuation coefficient is equal to 1. We don't need to calculate it. So now it is even easier solution. We just take this relationship between the attenuation coefficients for yttrium and strontium and multiplied it by half count rate for strontium. And thus, in the first case, in the case of 64 hours, we will obtain this count rate, 2133 CPM. So the total count rate of the sample after 64 hours will be 3600 plus 2133. So it will give us 5733 CPM. That's counts per minute. And for the second case, when it is 128 hours after the purification, the count rate of yttrium will be also this ratio that multiplied by the 0.75. Simply, we can just multiply this number by 1.5 because it is difference between 0.75 and 0.5, and it will be, let's say, 3200 CPM, and thus the count rate after 128 hours will be 3600 plus 3200 CPM. It will be 800 CPM. What is important in this task? First of all, it is the difference in attenuation coefficients for strontium and yttrium. Why these numbers of mass attenuation coefficients are so different? Because I didn't write it here, but the maximum energy of beta particles, max, for strontium is 546 kiloelectron volts. And for yttrium, this maximum energy of beta particles is 2274 kiloelectron volts. Thus, you can clearly see that the mass attenuation coefficient is much smaller for the beta particles with high energy. Again, that means that the beta particles with high energy can easily penetrate in the matter. The higher the energy of beta particles or any of the particles, gamma quanta or even alpha particles, the higher their energy, the more penetration ability they have. And vice versa, the higher the energy, the higher the penetration ability, and that means the smaller the mass attenuation coefficient. So matter stops less efficiently the particles with high energy. Also, you can clearly see that the range or maximum range of the particles, beta particles in this case, differ significantly for these two cases. Again, the higher the energy, the longer the distance that particles can penetrate inside the matter. It's not only a distance of penetration of these particles, but it is also it also affects the attenuation coefficients when we calculate the absorption of the particles emitted by different radionuclides. You can clearly see that for strontium, the attenuation coefficients, that means the percent of particles that go through this distance, is smaller than for yttrium, that for particles that are released from yttrium-90. So it is always important to remember the differences in the penetration ability, and thus how many particles can reach, for example, human body when we are working with the beta-emitting radionuclides. This penetration ability depends mainly on the energy of the released beta particles. Thus, when you have the information on the radionuclide composition of your material, then you can understand what is the penetration ability what is the maximum range of the particles that are emitted by your sample. So I hope it was clear for you, and these two tasks was all for today. So I will send you again the homework that I will expect to get in a week. Goodbye.